Unraveling the matrix, how rotations transform in 3D space. So carrying on from last question, problem A15 tells us to, in the usual bases I hat, J hat, K hat, construct the matrix Tx representing a rotation through the angle theta about the x-axis, and the matrix Ty representing a rotation through the angle theta about the y-axis. Now, suppose that we change bases such that I hat prime goes to J hat prime goes to negative I hat, and K hat prime goes to K hat. So same thing. Construct the matrix S that affects this change. So we're trying to find the matrix that makes this transition happen. And check that ST𝑥S inverse and ST𝑦S inverse are what you think they are and what you would expect. So, like we saw last time, in this transformation, the x and y axes correspond to a standard two-dimensional graph, while the z-axis extends perpendicular to the page, as we see here. So, a counterclockwise rotation by an angle theta about the x-axis is visualized as such. As you see, we're rotating about the axis here, which sends y down some amount theta to the new y prime, and z down some amount theta to z prime. Now, using the same procedure as last time with the direction cosines, we know that the angle between x prime and x is equal to cosine 0 because the x-axis and the x prime axis are laying on top of each other. So that tells us that the axes remain unchanged in this transformation. Now, between x prime and y, x prime and the dashed y here, they're still sitting at 90 degrees, so that is 0. Further, x prime and z, well, x prime and z happen here, so once again, 90 degrees, and we're 0. Running through the other components, y prime and x give us 90 degrees. Y prime y, that gives us an amount cosine theta. And then we have y prime and z. So remember, y prime's here, z's right here. And if this thing was, these dashed lines were 90 degrees to each other, this has to be 90 minus theta. Okay, so that's where this comes from. Sum and difference of the trig identities, sum and difference gives us sine as an equivalence. Now z prime and x, kind of the flip-flop of this one, gives us 90 degrees. Z prime and y, we see that the original y, the dashed line here, is this 90 degrees plus the theta rotation from this rotation about x. So that gives us 90 plus theta, which the sum and difference, once again, yield a negative sign. Following that, we have the difference of angle between z prime and z. That's just an amount theta, so our cosine theta is what we need. And once again, the direction cosines give us everything we need to unlock this rotation matrix. So what we say here is that the transformation or rotation matrix x about x rather, is this. Now, we can have the same continuity of thought geometrically if we consider that in this case, since we're rotating about the x-axis, the I hat prime equals I hat. So that's the 1, 0, 0 there. J hat prime is composed of some part in the old J hat in the old Y direction, and now some part in the now Z direction, the old Z direction. So we have cosine sine, cosine sine. K hat, well, the new K hat is some negative part in the the new K hat, the Z direction, is now some negative part in the old Y direction and still some amount in the old Z direction. So negative sine, cosine there. Let's compare this to what we saw last question when we rotated about the Z-axis, to which we saw we still had a cosine sine, negative sine, cosine. So we have to have all four of these elements just where we displaced. Notice that the one goes on the rotation axis, one goes on the rotation axis here, and we just keep this kind of argument style going like such, so long as we're counterclockwise rotation. Now, if we're y-axis aligned, like what we're being told here, we see we run through the same thing. Z gets swept out, x gets swept out by some amount theta. So we're running through the same process. For our x's, the difference in angle between x and x prime is just theta, which is what we see there. Note that it's still pointed somewhere in the positive x direction, so we're good, but we just don't know how much, and we'll deal with that when we talk about the geometry of it later. Then we have x prime and y, that's still 90 degrees to the y-axis. Then we have x prime and z, so because our angle here is still 90 degrees, and this is theta, we have to add 90 plus theta. Once again, sum and difference comes in and gives us our negative sign. So we got two of our cosine sine components that we need. For the y's, run it through the same thing, 90 degrees. Y prime is sitting on top of y, so that's cosine 0, gives us 1. And then the 90 degrees to the z, so we're good there, makes sense. Now we see that for the z's, z prime here with respect to x, that's going to be 90 minus theta, because that's this 90 degrees minus that gives us this remainder here. Once again, sum and difference give us a sine. Then we see that z prime to y, 90 degrees again. Z prime and z, difference of cosine, so we're good. So putting this all together for the y-axis aligned, we see we still have the kind of same construction. Cosine, a negative sign, sine, and a cosine. But we see that we have a 1 right here on the rotation axis. So geometrically, we know that if we're looking at the new axes in terms of the old axes, we see that the new x direction is some part x and some negative part in the z. Because remember, we're swept out into that negative z direction, hence cosine, negative sine. J hat prime and j hat, well, they lay on top of each other, so that's why we have a 1. The new z direction, k hat prime, is some part now in the old x direction and some part in the old z direction, so sine, cosine respectively. Now, again with this quick note that we saw last time about the prime axes being the rows, and then some texts put them as columns, so on and so forth. What we really have to understand about these constructions here is which frame are you referencing? Are we saying, what do I multiply to get to the new frame, i.e. the prime frame, versus am I multiplying to get from the prime frame to the old frame? And so what we see here is that when we look at this versus the column construction, we see that this puts it in reference frame to the new I hat or the new prime axes, right? So I hat prime, we see we list in the row. But if we look at the old axes, the I hats by themselves, we see that we have a part of the new I hat with cosine relation, so that goes there. But over here we have another I hat that's related to the new K frame, and that goes here. So cosine from there, sine from here, and we get the same thing. These rows and columns are interconnected, it's just which frame are we looking at, the prime or the old frame? And of course, once you kind of see these patterns emerge, you can't unsee them, and we can see how the construction happens. I'm pointing this out now because when we go to construct the similarity matrix for the multiplication later, what we're going to end up finding is that we're going to need to use the old frame in terms of the new one, or the new one in terms of the old one. Both flip-flop, one's a row, one's a column, so as long as you can see it in these geometric traits here, we can use it in the next parts as well. So central rotation matrices are used in all branches, E&M, classical, quantum, robotics, computer graphics, all of that. It's worth revisiting all the three that we have for the axes aligned rotations. As such, we saw last time that the TZ or the lambda Z transpose was given as such. So we see we have, once we take the TZ and we put them in columns like what we traditionally see in most books and definitely most online resources, this is what we get to. Okay, so as a result, what we see here is when we compare this, again, Z is untouched, Y is untouched, X is untouched, and we still see this, collection of cosine, negative sine, sine, cosine, cosine, sine, negative sine, cosine, cosine, negative sine, negative sine, cosine. It's all the same kind of idea, except all we're doing is shifting where the 1 is, and the negative sign has to follow on which of the compensating directions. Pretty darn cool. Okay, but in this problem, we're told about a change of bases, and this is where the column versus row thing needs to be put into a new perspective. So because we're told that our I-hats now get changed, our new I-hat primes are the J-hats, and our new J-hat primes are negative I-hats, and of course K-hats on top of the old K-hat. What we can say is that from equation A.15-Symmetry, which is a column vector construction, we know that we can find the old bases in terms of the new bases and vice versa. We just have to use this linear combination construction where the old base EG or EJ right here is constructed of the new bases with some amount of some scalar amount, which gives us the instructions on how to transform them. Okay, so what this is saying is that to get the old bases, we need to multiply by these coefficients in order to find out what the instructions are. For example, if we take j equal 1, which gives us to our unit vector 1, E1, which is the I-hat direction. So putting the I-hat into column vector notation, which is 1, 0, 0, as we see here, we have to ask ourselves what component S11, what amount of S21, and what amount of S31 from our new bases. So we see that I-hat prime is J-hat, so that goes to 0, 1, 0. J-hat prime is now negative I-hat, so we put a negative 1 there. K-hat prime is K-hat, so we just leave that there. What values do I put on the S11, S21, and S31 in order to get this value back? So we look at this first component. We see that that's a 0, so that's not going to contribute anything. That's a negative 1, so we're going to have to undo that negative 1 in order for it to contribute. And then this is a 0, so it doesn't contribute anything. As a result, by inspection, unless you want to create a linear system from this, which you absolutely can, and then take inverses, blah, blah, blah. We'll save that on a different video where we can talk about spanning sets, things like that. But what we see here is that this needs to contribute 0 because we don't have any contributions there, and this isn't going to contribute to constructing 1. So the only way that this can contribute is by a 0 scalar. Similarly, this one, to undo this negative 1, we have to multiply by negative 1, and that's how we get a positive 1 here, while maintaining 0, 0 here. Lastly, following the same argument from S11, we see that the only contribution this needs to give in order to reconstruct this is with 0. This is a 0. The only way to get out a 0 with a 1 multiplying by something is multiply by 0. So we're good to go. And using this inspection method, we can find out all components of the transformation matrix S. So running it through j equals 2 for the y component, we said our old bases is 0, 1, 0. What do I need to add here for S12, S22, S32 to maintain this? Well, we see that this needs to be a 0, this needs to be a 0. This is the only one that can contribute anything. As a result, we see that S12 needs to equal 1, 22 needs to equal 0, and S32 needs to equal 0. Lastly, our last component, j equals 3. For E3, we know that that's the z-hat direction, or the z direction, or k-hat, whatever notation you want to use. Nonetheless, we have a 1 in the last component and a 0 in the first two. Since this has a 1 in the middle component, it needs to go away. Since this has a 1 in the upper component, it needs to go away. And then we just need to use this and multiply by 1, and we see we get our components there. Now, putting this all together, we see that we have S11, so blue ones all in the first row, green ones in the first column, green 2s, green 3s, blue 2s, blue 3s, so we get our whole construction here. And note that what we end up with is an encoded instruction set, okay? So what we see is that we need the old bases can only be composed of one of these new bases here, -1, and so on and so forth. So we see we have everything we need from computing these column-wise. Okay, so you see how we have 1, 0, 0, put that here. 0, 0, 1, put that here. And this is the column construction as we've been trained to see with the quantum mechanics book. Now, let's take a different approach to this and kind of tie it to what we might have expected geometrically. So note the form, to form the column vector perspective, from the column vector perspective, excuse me, this looks like a stacked column vector if we wrote the original bases in terms of the new ones. Okay, so if our I hats that we had originally go to a negative j hat construction, right, versus putting this negative over here, what we see is that this goes to this column here. Cool. So that's why we have a -1 there. J hat came from I hat prime, which is what we see here. So a 1 right there for our second column. K hat stays on top of K hat, so we're good. So in the column vector perspective, this is how we can construct it without having to run through finding the components that way via inspection. Now, on another note of interest here is that the column vector construction, we might use Tx and Ty formulation, but we could construct the S matrix via row vectors just the same way, except that the rows are made from the new bases. So here, as we see, I hat prime is green here, but it comes from J, right? So I hat prime goes to J, and we see that if that's the case, we have a 0 on our I prime row. We have a 0 for our I prime here. We don't have any old I prime or I hat directions here. We just have a J hat direction and a 0 here. Similarly, J hat prime goes to negative I hat. So this is what we would expect in reverse. Okay, so when we're asking ourselves that, we need to put a -1 in the I direction and a 0 everywhere else. K hat on top of K hat, so we're good there. But nonetheless, you see these are the same exact matrices just from a different perspective. So however you want to construct it, just make sure you stay consistent. Are you going to be in the row perspective or the column perspective? Do you need to take a transpose or not? Either way, with the orthogonal style construction, we should be good to go. You just have to be careful on how you're applying it. Now, naturally, when you have a coordinate transform, it feels better to run this way because you're starting in an old frame and going to a new frame, hence the prime, and that's why we see the construction there. However, when we're asking how we get the prime notation from something else, that's when the row perspective can happen. And since we're looking for how does this matrix make the prime, this construction works just as well. Hence the difference in subscript, you have t versus lambda. Now the direction cosines work on the lambda concept of we're trying to get to the new prime. How do we get there? From what multiples of the old bases do we have to have? So that's why it works on this, and we're good to go. So a little clarification there. So moving forward, now that we need to get into the actual work of this problem, now that we've constructed everything, the inverse of this matrix can be found from Gauss-Jordan style elimination, where we augment the S matrix with an identity matrix and solve it down to reduced row echelon form. Or we could use cofactor forms like we see in equation A.15-Symmetry, where the inverse is equal to 1 over the determinant times the conjugate, or not the conjugate, but the transpose of the cofactor matrix, where the cofactor matrix C is defined as such. Note that we have our plus minus plus structure again. So we have all our signs here with the what we call minor or subdeterminants. So cross out the row, cross out the column, and we see we have a bunch of mini determinants here. Now, because we have so many ones or so many zeros mixed in with ones, most of these values are going to be 0. So let's see what we get. So if I evaluate my minor determinants, taking upper left to bottom right, upper right to bottom left, crisscross, 0 times 1 is 0, 0 times 0 is 0, so 0 minus 0 gives us this. If you do that for every single one of them, you see this is the algebra for it, and it simplifies into this exact same matrix. Now, how convenient is that the cofactor matrix is exactly what we started with? That being said, taking a transpose of it gives us this. Now, what's interesting is that after we apply this formula here where we take the subdeterminant, multiply it by the transpose, which, by the way, if we're going to take a determinant, take it about an easy row, right? So I'm saying go about the first row here because we had a 0, 1, 0, negative here. So this -1 is that -1, 1, 1, crisscross, that's 0, 0. So we see that the two negatives there cancel, leaving us with the division of 1 over 1. Hence, 1 times this transpose gives us this right here. What we've effectively shown is that S inverse is orthogonal to S because the transpose is the inverse. So we're good to go. And it's because of this orthogonal style construction that it doesn't matter really if we line up things with the row vector construction or column vector, because we can take transposes with ease and use them as we see fit. So now getting to the heart of the question with the grunt work done, the task of this question was to see if these transformation matrices acting on the rotation matrix is exactly what we expect when we change bases. Okay, so since S causes a change of bases, we see that putting the S matrix here, its inverse, which again, just to highlight, it's a transpose of this matrix, so we're orthogonal matrices. With the TX rotation matrix, again, this is the transpose of the lambda X matrix, just to make sure we're all in the same construction, since this book and many others like column constructions. We see here that after one multiplication, lots of zeros, and all we did was shift out where our cosine and sines go. One more leads us to this, where we have negative signs going a little crazy, but we're still good to go nonetheless. But let's note here that this multiplication, this transformation matrix, changes our 1 here, which tells us that we had something acting on the I prime from the J perspective, from the Y perspective, and now we put that 1 right in the middle. So automatically, alarm bells should be going off in your head that this looks like a Y rotation matrix, especially with the cosines on the other two diagonal spots. What we need to do now is a little bit of form matching to say, look, this negative here can go inside because sine is an odd function. We can append negatives here on cosine so long as I put a negative here and on the two negatives here. Because we know that cosine is an even function, negative arguments don't matter to it, so we're good there. And so what we can do is say that, okay, well, this plus sign looks like two minus signs. Sine being an odd function, I could put one minus on the inside, keep one on the outside. This minus goes on the inside, so I get rid of all minuses except for this one, which tells us that we're of the form ty with the negative theta. So rotate it in the opposite direction per se. That being said, this is exactly what we'd expect if our S sends our I hat to the negative J hat. So kind of expected that. And we'll touch on that more in just a second. Lastly, we still need to see how the this S matrix transformation affects the rotation matrix for Y. So note here that we have our Y rotation again. Run it through its gauntlet. We see that after one multiplication, our 1 here gets shifted to an X position, but after another multiplication, it gets shifted to the top position. So what we see here is that the 1 ends up in a perfect spot for a TX or the X aligned rotation. Very freaking cool to see. So the question of, does it actually make sense? Well, yes. This result aligns perfectly with our expectation. The change of bases transforms a rotation about the x-axis into a rotation about the negative y prime axis, while a rotation about the y-axis becomes a rotation about the x prime axis. Or in other words, j has to go to, the old j hat has to go to an I hat prime. So that's the same as taking the similarity transform here on the y rotation, and that gives us an x. So j goes to x, we get our tx rotation. Pretty darn cool. Now the one that's a little clunky because of the minus sign, I hat goes to negative j hat prime. Well, if we see that we start on the I, which is x, we need our tx. The similarity transform happens here. Then we see that we get a ty with the negative. We're good to go. The negative is incorporated in that. And that's really freaking cool. Who would have thought that this would work out so nice outside of the people who made it, or really observed it, and then formulate, and then made it a formulism that we use? This is just simply incredible. Like, geometric is coming into play, we could see it, and we're not just having to deal with some arbitrary hieroglyphic linear algebra language. So this is really amazing, and I'm having so much fun making this because it revisited all the little things of why we liked matrices, why we learned to use them and utilize them, because of things like rotations. And if you take an abstract algebra class, you have compositions of rotations, and they form a group, the group of rotations, and then eventually you see how that ties into the bigger structure of things like the isospin groups, things like that, SU2 or SO or the SO groups, special orthogonal groups, special unitary groups, unitary one groups, things like that. All those things come together and you form the SO3 or SU3s, things like that. Very, very useful to us to get our hands sufficiently worked with this ground level stuff, because when you get to higher levels, you're going to be happy that you had such a firm foundation with this. Very, very important. Holy moly, that was a ton of fun. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is so much more to uncover, and I'd love to have you along for the journey. I also want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.